A very good afternoon and warm welcome to this live session. I am Dr. Vaibhav Pandit, and today we are going to discuss the topic titled Image Segmentation Thresholding. So this is our last session for solving the academic doubts related to the topics of image processing subject here. So already we are covered with several of the sessions where I have addressed many of the image processing techniques. The first, that it was image enhancement based on to the spatial domain and onto the frequency domain we have dealt with. Then image restoration we have seen, color image processing we have seen, wavelets and multi-resolution analysis we have also addressed, image compression also we have covered, and in one of our previous session we have gone through the understanding of morphological image processing here. So image segmentation is like the same, the fundamental task for having the digital image processing accomplished here. So based on to the image segmentation, here I am going to first of all solve one basic problem that will provide you the simple idea behind the thresholding, which is the most popular in the image segmentation here. So let us first of all have one problem. So here we have the simplest problem statement. The problem statement is, consider the image segment. Image plane is provided to us in the problem statement. Here it is. And now we are asked to have the image segmentation based on to the histogram here, and the segmentation should be there in two parts here. So to look at this straightforward problem statement for image segmentation by thresholding method, you see the given image segment is just a representation with the help of a matrix, and here you see there are 8 columns and 8 rows. So I can say the given image sample is of the order 8 by 8. So there are total 64 pixels arranged into 8 rows and 8 columns of this particular image sample here. Now for this particular image sample we have to consider the histogram. So what is histogram should be known to you people. I have also addressed one of the session to take the histogram equalization. My other lectures associated to the details of histogram are already available on the online platform that you can attend, and if you know, that is quite better here. So considering the histogram for the given image, we have to perform image segmentation so that we are having the resultant image having the two regions here. So let us solve this particular problem using two steps here. So now in the step number 1, we are going to have computation of the histogram. So what is histogram should be known to you people. The simple and the brief definition I provide you here. The definition is, the histogram of any image is the plot of the frequency of occurrence versus the gray level. So now you see the frequency of occurrence means what? See, we have been provided the image plane which is of the order 8 by 8. So you can go to that particular slide where you see there are the pixel intensities arranged into 8 rows and 8 columns. So total 64 pixels here we have. So if you see that image plane, the first row, first column element, the pixel intensity there it is represent to be 128. As we proceed in the same row, we have 128 two more times, then we have 2 times 64, then 32 two times, at last we have 8. In the second row there it is 64, 64, 128 three times, then 8, then 32 two times here. So how many number of times a certain gray level or the pixel intensity has there in the image plane, so it should be counted, and that particular count will give you the frequency of occurrence, the frequency of occurrence for a certain gray level. And when we plot it, so it is nothing but the histogram of the given image here. So the histogram of the given image can also be represented with the help of a tabulation or a graphical plot here. Now you see, the image plane that is provided in this problem statement is having only the 4 pixel intensities or the gray level. See, the pixel intensity 128 is there. Next to that, there it is the use of 64 as the pixel intensity, gray level, so it is 32 and 8. So these are the only 4 gray levels used into the input image here, which is to be segmented here. Now when we have counted how many number of times 128 has there in the image plane, so the answer to this question is, after count, it is 22 times. Whereas in the same image plane 64 pixel intensity or the gray level has occurred 24 times here. So 32 pixel intensity has occurred 8 times and 8 pixel intensity has occurred 10 times here. So you can go on counting this by row wise or column wise, whatever the way you prefer here. So when I just have such a plot on the horizontal axis, if I make 4 markings here, see, on this particular axis the marking of these particular gray levels should be serially, right from 0 to whatever the maximum pixel intensities we have in the environment of this image plane here. So as we have 8, then 32, then 64, then 128. So in that regard you should have marking on the horizontal axis. So the horizontal axis is having the gray levels plotted here, whereas the frequency of occurrence should be there on the vertical axis here. So for 8, here it should be a point. For 32, for example, here it should be a point. For 64, somewhere here. And for 128, somewhere here. So this particular plot is nothing but the histogram here. So histogram we are now well aware about for the given image sample. So this was the step number 1. Now we are going to perform step number 2. In the step number 2, we are going to perform the exact image segmentation based on to the histogram that we have available from the step number 1 here. So from the histogram that we have, it is quite obvious that the gray level which occurs at a least time here, so that it is 32 gray level, it has occurred only 8 times, whereas the gray level representing 128 as a number in that matrix has occurred 22 number of times, 64 has occurred 24 times, 8 has occurred 10 times, whereas 32 has occurred a very small number as compared to the others, that it is 8 here. So now based on to this observation from the histogram that we have computed from the given image sample, we can fix the threshold value. So the threshold value should be equal to 32 here. See, our today's topic is image segmentation thresholding here. So threshold is something like a cutoff here. So here for the given image sample we are selecting the 32 value to be a certain cutoff, to be a certain threshold. Now we can put up certain criterion. So whatever the pixels are there having the intensities greater than that, we can apply certain rule. Whatever the pixel intensities those are less than that of the 32, we can apply another rule. So this way we can perform the image segmentation, because the motive to have image segmentation is to separate out the different regions those have collective similar property within them. So in simple language I will say, just to separate out the objects from the background into the image scenario is simply the image segmentation here, or to separate out the two objects from one another here. So as we have fixed the threshold value equal to 32, now we can apply the rules for dividing the image sample into the two regions. So let us define region number 1, where the gray level, which is also known by the pixel intensity, is less than or equal to the threshold value 32. Whereas the region 2 can be defined as those all particular pixels to be collected where the corresponding gray level is greater than the threshold value 32 here. So from the number 32, here it is the separation into the region 1 and region 2 of the image here. So if I just assign the numbers for all the pixel intensities, those are greater than or equal to 32, I assign 1 at the same location in the image plane. The corresponding row number and the column number is to be checked thereupon. Whereas those pixel intensities are greater than, so here it is for the first region, it should be less than or equal to 32 here, and for the second case it should be greater than 32. So I will write 2 in that particular place. So if you take another, again the same dimension matrix 8 by 8 here, so it will be the image after applying these particular decision rules of the thresholding here. So it will be like this. In the first row you will find 2, 2, 2, 2. This is 5 times. Then we have 3 times 1. So this is all with respect to the two rules that I have shown on the previous slide. In the next row as well, there it is 2 for the 5 times and 1 3 times here. In the third row we have initially 1 2 times, then rest of the 6 entries are with 2 here. So 2 represents a certain region here, 1 represents a certain region here. We have to group them all. See here, if I collect all these 2's like this, so this is one kind of the region that I am having collected here. So here I am outlining all the 2's, possibly all will be collected. So this is what the region 2 here, a bigger region as compared to the another here. So here a shading can be also provided. So in the given input image, this is one region, and if you collect ones here, those are remaining, this will be another region here. So this way we have solved this particular problem using thresholding technique of image segmentation here. Now I hope the picture is clear to you people, the topic that we have been dealing, that is image segmentation thresholding here. So as we have the times, as we have time, let us address few of more details with respect to this thresholding technique for image segmentation. So here I will be addressing foundation of thresholding that will clear all your ideas with respect to this technique, image processing technique. So here it is, foundation of thresholding here. So to understand the foundation of thresholding, let us have a consideration that we are having one image. So generally we denote the image for mathematical representation, symbolic notation, f of x comma y. So x and y are the two spatial dimensions. Here you can also take to be the number of row and the number of column here, and f will be representing the pixel value or the intensity value, or also known to be the gray level at that particular location here. So if we have the image sample, so as we have just done in the preceding problem, we can have the histogram for it. So the consideration of a certain image is there, and based on to the image we have the gray level histogram that also we visualize here. And the consideration is of course there that the image is composed of the light objects onto a dark type of the or the dark colored background here. So now here it is in such a way that the object and background pixels have gray levels grouped into the two dominant modes here. Here we visualize the histogram here. So this is the gray level histogram that can be partitioned by a single threshold. The example we are going to discuss here. See, the histogram definition I have already made it clear to you people. So if you are having 0 here, so 255 should be the maximum value on the horizontal axis representing the different gray levels here. And on the vertical axis, as we discussed earlier, how many number of times a certain gray level has occurred into the given image plane. So that we plot. So here it is the frequency of occurrence of the gray levels on the vertical axis. So for the considered image, here it is the scenario of the histogram where we can have two groups here. So the two groups can be separated with a certain point that we can select to be a threshold. So the earlier example that we discussed was of this particular type where the gray level histogram can be partitioned by a single threshold here. So because of this particular reason, one obvious way for extracting the objects, which is the motive of image segmentation. So the extraction of the objects from the background is to have selection of a threshold T that separates these two modes here. In the earlier problem, the threshold was at the value 32 here. So at any point, the point can be represented by their spatial coordinates x, y, for which the pixel intensity f of x, y is greater than t. We will call it to be the object point, and if the condition is false, we will consider that particular point to be a background point. So this is what the rule with the help of thresholding here, and the case is here a single threshold here. Now we move on to increase the number of thresholds here. So let us have one more figure that will illustrate you the visualization of another histogram for another kind of the image. So the figure shows slightly more general case for this particular approach where three dominant modes, those we can separate out with the two threshold values for characterizing the image here. Here we visualize. So here you see the gray level histograms that can be partitioned by multiple threshold levels here. So here I show you the gray levels plotted on the horizontal axis and how many number of times that particular gray level has occurred into the image plane that we have plotted on the vertical axis here. So now you see the three groups, the three prominent groups. Here I just encircle them, and the separation of a group from another, that is with respect to these values of the gray levels that we can treat as the threshold values. So as in the beginning problem there it was only one threshold, the value was 32. It is not the case here. Here we are having the two thresholds that separates the image plane into the three modes or the three groups here. So for such a multi-level thresholding, we can have the classification of the point with the multiple rules here. So let us have for this particular type of the histogram, we have the rules one by one. So there it is identification of one object class if the given or the considered pixel intensity at the location x, y is greater than t1 and less than or equal to t2 here. So this is one region or one object you can say. Next to that, we can go for identification of the other object class if the pixel intensity f of x, y is greater than the threshold t2 second threshold value, and we can have the identification of the pixel to be from the background if the pixel intensity f of x, y is less than or equal to t1 here. So in this representation you see there it is the use of both the threshold values here. First threshold value T1. So all the pixel intensities less than the first threshold occurred onto the gray level axis to represent the histogram is identification of the background here. So this is not intended particular portion into the image plane here. Now here we have the region that is having the pixel intensities between the two threshold values, greater than the first threshold but less than the second here. So this is one region, and the another is having the pixel intensity greater than the second threshold. So obviously they are greater than the first threshold as well. So this is another object here. So this is a set of rules for the multi-level thresholding here. So here in general, the thresholding can be viewed as an operation, image processing operation, that will involve the tests again a function of the form. Here mathematically the function against which we have to perform that particular operation we visualize by this mathematical expression. So it is capital T. So this capital T is to be operated on to the factors. Those are represented inside this bracket here. So first one is the small x, then small y. These are the two spatial dimensions here. So with the identification of x and y, we can get to the exact location of the pixel under consideration. There it is the use of p as a function of these spatial coordinates x, y, and along with f as a function of again x, y, the spatial coordinates here. So in this representation of the mathematical way here, f of x, y is the general representation of the gray level image here. So f is the intensity at the location x, y, whereas p of x, y is representing some kind of local property at that particular location here. So for example, the average gray level of the neighborhood centered onto the pixel x, y, if we consider that, you can treat it to be the local property p of x, y. So based on to these four factors, the two spatial dimensions or the spatial coordinates you say x, y, then the pixel intensity f, that is basically a function of these spatial dimensions, and the local property, for example averaging for a certain neighborhood. For example, the dimension may be 3 by 3, 5 by 5. So these we have practiced for spatial type of the filtering, for image enhancement, for image restoration also. So that way. So this is what the thresholding function, that is involving the test against a function capital T as represented by this particular equation here. So now what is the output image? So to describe the output image with the help of the symbolic notation, we can call the output image to be a thresholded image. So the input image, generally what we represent f of x, y after thresholding, will also be again a function of the spatial dimensions x, y. So let us represent it as g of x, y here. So we can define g of x, y. Here it is, to opt the value 1 if the f of x, y, that means the pixel intensity, is greater than the threshold capital T. Otherwise, if it is having f of x, y less than or equal to capital T, so it will be equal to 0 here. So now the pixels will be labeled 1, and based on to this particular threshold value, we can recognize those particular pixels to be a part of the object here, whereas the pixels labeled by the value 0 based on to the above rule here will correspond to the background into the image. So here it is, the identification of what is the background region and the object region here. And now there are three very important points corresponding to the threshold. These are basically the subtypes of the thresholding here. So when we have the threshold as denoted by capital T, depending only and only on to the pixel intensity denoted by f as a function of x, y, the threshold is called as a global threshold here. Whereas if the capital T depends on both f of x comma y and p of x comma y, the threshold is called as a local threshold. So see the distinguish between the global threshold and the local threshold. Based on to this, we have more details. Global thresholding for image segmentation, local type of thresholding. So there are different issues associated to the use of such different types of the thresholds here. And at the last, if the capital T depends on the spatial coordinates x and y, and that time the threshold is called as a dynamic. It is also sometimes also known by the term adaptive type of the thresholding here. So these are the subcategories you can treat for thresholding to perform image segmentation here. So here the foundation of thresholding we are covered with. As we have still the time here, now we can address while we perform the thresholding operation for carrying out the image segmentation onto the input image, what is the role of illumination here? See, in the beginning lectures, when I started to teach you the way with which the image is formed here. See, there are certain imaging sensors, and because of those particular imaging sensors, the energy is captured and recorded in the form of the image. So thereupon, there it is requirement that the objects into the scenario for which we are intended to capture the image, to save the image, they should be illuminated by a certain source of electromagnetic energy here. So light is the best example of the electromagnetic energy. So based on to the type of the source illuminating the objects in the scenario, we have the two types here. One is the optical and another that means passive and active here. When we have the source with us, so that is active. When we don't have the source with us, that is passive, and mostly it is having the optical type because sun is the natural source of illumination here. And if we have a certain infrared source, so that it will incident its electromagnetic radiation onto the object and catch the corresponding reflection back, so it is the active type here. So it is somewhat the type of the microwave imaging here. A lot many applications I have discussed in the beginning lectures here. So that time the image formation model we have discussed. We had the representations for what is the amount illuminated for the objects and how much is the amount of the energy we have received as the reflected portion here. That will discuss near. So let us have a recall of that particular simple model where we have the image denoted f of x comma y, and it is basically constituted by the two components here. One is the reflectance component denoted by r of x comma y, and another one is the illumination component here. So the illumination component here it is represented for symbolic representation I of x comma y, and the reflectance component r of x comma y here. So now let us initiate a discussion for the effect of illumination while we are performing the thresholding operation for image segmentation. And let us have the consideration that as just now we have seen the type of the thresholding here. The thresholding can be global thresholding, it can be local thresholding, it can be dynamic, also called as adaptive type of the thresholding. So first of all, consideration of the global type of the thresholding here, the simplest one here. So for example, let us have a consideration of a computer generated reflectance function recorded here that we visualize into the figure. So let us consider this to be the figure part A here. So computer generated reflectance function, here you see a certain background and a certain region having the different pixel intensity recorded here. Now corresponding to this particular reflectance function recorded as we can visualize on the digital screen, we can have the plot of frequency of occurrence of the pixel intensities versus the gray labels here. So it will be obviously the histogram here. So the corresponding histogram of this particular function we can have as figure B, that will clearly be a bimodal, that means having a separation into the two groups for the pixel intensities, and that can be partitioned easily with the help of a single threshold, the case we discussed at the beginning of this particular lecture, based on to which we have solved a simple problem as well here. So here you visualize the corresponding histogram. As you see, there are only major two kinds of the pixel intensities here. So these are the two prominent groups for the pixels, those form the image sample here. So on the horizontal axis we have the gray levels that you see for the 8-bit environment, the concentration here it is. So we started at 0 and the maximum pixel intensity is 255. So major group of pixels here it is centered around 70 to be the pixel intensity, and another prominent less than the earlier one, it is centered around, for example, 175 here. So now if we have the concentration of the illumination function, now you see the figure A and figure B, both you have visualized for the reflectance function. For the image to be represented as f of x comma y, there are two components we have discussed. First one is the illumination and second one is the reflectance here. So the visualization into the figure part A, that it was computer generated reflectance function, and here it is the histogram of the same reflectance function. Now we talk about the illumination function, the another component here. So let us have consideration of another synthetic or computer generated illumination function. Here we visualize. Now you see there it is a gradual change into the pixel intensity levels as we move on from left hand side to the right hand side here. So these are changing. The values are having a linear variation as we go from left hand side to right hand side here. Now let us have a consideration of what will be the effect if such illumination function is there onto the reflectance function, because the reflectance function is more important to us because it is what the energy that has been captured by our imaging sensor, and that is supposed to be recorded here, and this is the illumination function which is going to affect that particular energy here. So if we simply carry out multiplication of the reflectance function that we have visualized in two-dimensional form for the figure A by the illumination function that just now we have visualized into the two-dimensional plane for the previous figure part C here. So that time the product of those particular functions, here we show that it will be the next part of the figure here, and correspondingly we also plot the histogram for such a multiplication result here. So here it is the figure part D, where you see the product means a multiplication of part A is the reflectance function in two-dimensional visualization, and part C is the illumination function again into the two-dimensional visualization here. The corresponding histogram here it is visualized into the next part, figure E here. So now you see, because of the multiplication of the reflectance function by the illumination function, there it is a change into the earlier histogram. For the earlier histogram, we could have separation of the two dominant regions with the help of a single threshold value. That seems to be a difficult task in the current histogram here. So this is the histogram of the product image, the image that has been formed by multiplication of the reflectance as well as the illumination function here. So we have certain points for the role of illumination onto the thresholding procedure for image segmentation. So these are the points to be noted. The first one is the original valley that we saw, it was virtually eliminated here, making the image segmentation by a single threshold impossible task. Here we cannot separate out the two regions with a single threshold here. Now, this simple illustration is showing us that the reflective nature of the objects and the background could be such that they are easily separable. However, the image resulting from the poor illumination could be quite difficult to segment here. Now, let us consider a little bit of the mathematical background for this role of illumination onto the thresholding procedure here. So let us first of all represent the image to be processed for image segmentation to be denoted as f of x comma y, and it is initially having the two components, initial illumination component and the reflectance component here. So the reflectance component here we denote by r of x comma y, whereas the illumination component here we denote I of x comma y. So these are the two different components here. Now, if we take natural logarithm for the above equation here, so taking natural logarithm here we can have the representation. So z of x comma y will be the representation instead of f of x comma y after taking logarithm. So ln represent the natural logarithm. So natural logarithm of f of x comma y. So as we have the product of I of x comma y and r of x comma y, taking the logarithm, it will be having the addition of the resultants of the logarithmic representations here. So here we show ln of I of x comma y, whereas here it is ln of r of x comma y. So natural logarithm for the illumination function and the reflectance function. So they can be further denoted by I dash of x comma y, and for the reflectance part it is r dash of x comma y here. So with this particular consideration, if we have the probability background here, so from the probability theory, if this I dash of x comma y and r dash of x comma y after taking the logarithm are independent random variables, so that time the histogram for the image represented after taking logarithm as z of x comma y will be given by the convolution of the histograms, corresponding histograms of I dash of x comma y and r dash of x comma y here. And now if I of x comma y were constant, so that time I dash of x comma y would be a constant also, and its corresponding histogram would be a simple spike like an impulse function. The convolution of the impulse function, now if it is to be taken with the histogram of the r dash of x comma y, it would leave the basic shape of the histogram as unchanged here. But if I dash of x comma y had a broader histogram, the convolution process would smear the histogram of r dash of x comma y, yielding a histogram for the image represented by z of x comma y, whose shape could be quite different from that of the histogram of r dash of x comma y. So now the degree of distortion will depend on the broadness of the histogram of the illumination part here I dash of x comma y, which in turn depends on the non-uniformity of the illumination function. And when access to the illumination source is available to us, so that time a solution frequently uses in practice to compensate for non-uniformity is to project the illumination pattern onto a constant white reflective surface here. So this is supposed to yield an image that we generally represent as g of x comma y, the output resultant image, simply k multiplied by I of x comma y here. So here k is a constant and it will depend onto the surface, and I of x comma y is the illumination pattern as we discussed earlier here. So in this particular case, for any image denoted f of x comma y to be a product of I of x comma y and r of x comma y obtained with the same illumination function, will simply dividing f of x comma y by the output image g of x comma y will yield the normalization function here. It can be denoted by h of x comma y. So here we have h of x comma y is equal to f of x comma y divided by g of x comma y. So simply it will be equal to r of x comma y divided by k here, because I of x comma y will be cancelled out from the numerator and the denominator. So therefore, if r of x comma y can be segmented by using a single threshold generally denoted by capital T, so that time the normalization function h of x comma y can be segmented by the use of a single threshold of the value. Here the value it will be capital T divided by k here. So here I suppose this is enough discussion on to what is the role of illumination on the thresholding process for carrying out image segmentation here. After this, let us address few of the details with respect to the basic global thresholding here. So regarding the basic global thresholding, it is basically the simplest of all the thresholding technique, and it is supposed to partition the image histogram by using a single global threshold that we have denoted by capital T here. Now segmentation is then accomplished by scanning the image pixel by pixel and labeling each of the pixel as whether it is object or the background here, and it will depend on whether the gray level of that particular pixel is greater or less than that of the threshold value, the cutoff value that we have denoted by capital T here. And the success of this global thresholding methodology will depend entirely on how well the histogram can be partitioned here. So you should be able to get the exact histogram for the given image sample, so that time we can directly apply the criterion for the global thresholding and obtain the segmented image here. Now for the basic global thresholding, let us have a consideration of one example with the help of a visual illustration here. So we have figure part A having the original image. So let us have this original image, you see, and the corresponding image histogram can be visualized with the help of the second part of the diagram here. Now when we carry out the global thresholding having consideration of capital T to be a certain threshold which is midway between for this particular histogram here. So it is having the maximum gray levels and the minimum gray levels here. So if the midpoint is selected, the corresponding resultant visualization of the image after thresholding here we show you. Now you see the change here. So the type of the global thresholding that just now we have described can be expected to be successful in the highly controlled environment. That is a very important and necessary point. And the examples of such environments where the high control we can make are the industrial inspection applications, where the control of the illumination is usually feasible here. And the threshold in the preceding example that we discussed was specified by using a heuristic approach based on to the visual inspection of the histogram here. Now for the basic global thresholding, let us discuss out few of the steps, or we can also regard it to be the algorithm for processing the given image by global thresholding here. We have total 5 steps one by one here. So let us have the algorithm that can be used to obtain capital T for carrying out the global thresholding here. So there it will be the first step. The first step will be to select an initial estimate for the capital T. The second step it will be to perform segmentation of the image by using this estimated capital T. So this is supposed to have separate out two groups. Let us denote them by capital G1 and capital G2. So capital G1 is the region formed by the group of pixels. Those pixels are consisting the gray level values greater than the threshold value capital T that has been estimated here, and there it is another region G2 that is consisting of all those pixels with the values less than that of the threshold capital T here. So after this second stage, we are going to perform the third step, that is to make computation of the average gray level values denoted by mu1 and mu2 for the pixels into the corresponding regions G1 and G2 from the above stage here. Next to that, there it will be the fourth step where the computation of a new threshold value can be done. So for computation of the new threshold value, the formulation can be capital T will be equal to the addition of mu1 and mu2, which are the average gray level values, and which is divided by 2 here. So this is averaging of the averages here. Now in the last step, we have to make repetitions of the step number 2 through step number 4 until the difference into the capital T in successive iterations is smaller than a predefined parameter. You can consider this to be a tolerance denoted by capital T suffix 0 here. Now this is really very important stage to understand that this particular procedure is the iterative procedure here. To understand it in more details, let us have consideration of one example. So this example will have the visualization of the original image and the corresponding image histogram here. So here the example is of the fingerprint image. So for the fingerprint image, we have the corresponding image histogram also. So this is part A, original image, and this is part B, image histogram. Now you see on the left hand side the original image to be performed for the global thresholding for carrying out the image segmentation. We are intended to save the pattern of the fingerprint here, the miniature details that we see here, but we are not intended to store the background information, which is not at all required for whatever the application where this particular fingerprint image is utilized here as a resource. So in the corresponding image histogram, as we see the two prominent groups here, we intend to strike out the background here. So the application of the iterative algorithm that just now we have seen, which is of the 5 steps here, will be resulting into a value 125.4 after making 3 iterations starting with the average gray level and the tolerance capital T suffix 0